Let's start out with some reminders from the last chapter. What's the difference between empirical and molecular? Well, a molecular formula is exactly what the name implies. It's the formula of the molecule. It tells us exactly what a molecule looks like. It's the real makeup of a compound. An empirical formula is the simplest form that shows the basic ratio of elements in that compound. It doesn't tell us what the compound actually looks like, only how the general amount of the elements relate to each other. Now I want you to actually think about these next two here. How many empirical formulas can any single molecular formula have? How many times can you simplify something all the way down to its most basic form? And how many times can you scale up in a simple ratio? Pause the video, think it over, and then we'll move on. Well, what do you think? How many potatoes does this look like? How would we even begin to answer this question? To me, it seems like there's some information missing here. For one thing, we need to know how big this bowl of potatoes is. We can't see anything else in the picture to establish scale, so we don't know if this is a tiny little bowl or if it's a giant serving for the Guinness Book of World Records. We also don't know how big each potato is. But if I told you that each potato weighs 10 grams, that's a pretty good start. If I say that the mashed potatoes in this bowl weigh 80 grams, that's even better. At this point, we can do some simple math and figure out how many potatoes are mashed. We can take the bigger version of the potatoes, the mashed, and divide that by how much each potato weighs to figure out how many potatoes were actually mashed. In this example, we know the mashed potatoes weigh 80 grams, so we can divide that by the 10 grams that each potato weighs to tell us that 8 potatoes were mashed in this bowl. Somehow this is going to be pretty exactly how we can use small amounts of information to figure out a compound's molecular formula. To go back to the do now questions before, every molecular formula only has one empirical formula. You may be able to simplify a formula a few times, depending on which numbers you divide by to find a common factor, but an empirical formula is the simplest ratio, and there's only one of those for every molecular formula. However, it's completely different going in the opposite direction. This empirical formula CH4 could be what the molecule actually looks like. In fact, the gas methane is made up of 1 carbon and 4 hydrogens only. It could also be the empirical formula for a molecule with 2 carbons and 8 hydrogens, which is twice as large as its empirical formula in the simplest ratio. The compound could also be C3H12, which is 3 times larger. It could be C4H16, or C5H20, or C20H80, or any of these options of molecular formulas with a simple ratio of 4 times as many H's as the number of C's. Any of these things would match here, but it all comes back to this basic ratio right here. However many C's you have 4 times as many H's. The point is, any simplified empirical formula has an infinite number of possible corresponding molecular formulas, since a molecular formula is just some larger version of the empirical formula's ratio. And you can theoretically scale up this C4H4 ratio an endless number of times. That being said, how are we supposed to know how big a molecule actually is? Is it a tiny version of this ratio? Is it a little bit bigger? Is it enormous? To figure that out, we need to get some more information about our potato. To reiterate, and so you have this in your notes, any empirical formula has an infinite number of possible molecular formulas, which are just larger versions of the simplified ratio represented by the empirical formula. That being established, let's see how we can do this. To start, we need 2 pieces of information, what the empirical formula ratio is and the mass of the compound represented by the molecular formula. This is like when we need to know the mass of 1 potato and the mass of the bowl of mashed potatoes. Next, we divide the larger number by the smaller number. This is the mass of the actual larger molecule divided by the mass of its smaller, simple ratio version. It's the weight of the mashed potatoes divided by the weight of each potato. The answer to this calculation is how much bigger the molecular formula is compared to the empirical formula. Once we know how much larger it is, we multiply the empirical formula by this number to get a larger scaled up version of the molecular formula. And if that doesn't make any sense, we'll do plenty of examples next, so don't worry. Now that we have our steps, we'll try some examples. Put the directions over on the left side. You can always compare to these, but we'll just go through step by step and see how we can solve these problems. So first one, a compound's empirical formula is found to be CH2O. That means its simplest ratio of elements within that molecule is 1 carbon to 2 hydrogens to 1 oxygen, always in that ratio. So all we know about it so far is that for every carbon, there's an equal number of oxygens, and for any one of those 2 elements, there's twice as many hydrogens. Once we know how many of each element we have, we can see that it matches this, but that's all we know so far. It also tells us that the mass of the compound is 180 grams per mole. That means the big version, whatever the molecule actually looks like, weighs 180 grams if we add this thing up, if we add its pieces up. So right now we know that 1 carbon, 2 hydrogens, and 1 oxygen do not add up to 180. So we know that that's not what the molecule actually looks like. It's some smaller version. But when we know what the molecule looks like, we will be able to add everything up and know that it weighs 180. Unfortunately, at this point, we don't know what it looks like. So that's what we're going to do now. We want to determine its molecular formula, and we have these steps inside we can use. So number 1 says start with the empirical formula. We know from the question itself that the empirical formula is CH2O. That's its simple ratio. That's not going to change. Number 2 says find the GFM of the empirical formula. So we just now want to add up these pieces here and find what this mini version weighs. This is like finding what our individual potato weighs from before to help us figure out how many mashed potatoes went into the entire bowl. So we can add this up. We can do as we've been doing for a couple chapters now. We see that there's 1 carbon, and each carbon weighs 12. So 1 times 12 gives us 12 for the mass of just the carbon part of the molecule. We see there are 2 hydrogens. Each hydrogen weighs 1 according to our periodic table. So if we do 2 times 1, we know that the hydrogen part of the molecule weighs 2. We only have 1 oxygen. There's no number there, so it counts as a 1. So 1 times the 16 that the periodic table tells us each oxygen weighs, and 1 times 16 means the oxygen part of the molecule weighs 16. We add the whole thing up, and it's 12 plus 2 plus 16 gives us 30 grams for that basic version of our molecule. The simple ratio, the empirical form of this molecule, weighs 30. So that's our potato weight. That's what each individual potato weighs that we can use to figure out how many mashed potatoes were in the entire bowl. We've now done step 1. We've done step 2. Step 3 says divide the molecular mass. That's what they told us in the question, that the big version of the actual molecule weighs. Divide that number by the GFM of the empirical formula, which is right here. That's how much our simple version weighs. That was the 30 from step 2. When we do that, we do 180, molecular mass or molar mass, divided by the empirical formula's mass, the GFM of that. That was the 30. And we get an answer. We get 6. That means the big version of this molecule is 6 times larger than whatever our simple version is. The mashed potatoes before were, I think, was 8 times larger than one single potato. So we now know that 6 is how many times larger our actual molecule will find as an answer is compared to our simple ratio, our empirical formula. So to find that number now, we just do as step 4 says and multiply this empirical formula here by this number here. Scale it up by 6. Now we can't just write a 6 in the beginning because that just means there's 6 of the entire molecule. So instead, we just need to multiply each element in this formula by 6. So I'm going to multiply the C by 6, I'm going to multiply the 2 H's by 6, I'll multiply the 1 oxygen by 6, and scale it up, make it that much bigger. When we do that, we get a final answer of C6H12O6. The 1 carbon, 1 oxygen get multiplied by 6, and that gives us C6 and O6. And the H in the middle, there were 2 of them originally, multiply that by 6 to give us 12 H's. Our final formula is C6H12O6. If we add this whole thing up and find the masses of 6 carbons together, 12 hydrogens together, and 6 oxygens together, it should come out to be exactly 180 grams, which is what our question originally told us it weighs. That's our molecular formula. Find the little potato to find the big potato. Next one. Different question, same steps, you're going to do the exact same thing. Again, you've got the steps on the side written down to help you through this. Question 2 says a compound has an empirical formula of CH2 and a molecular mass of 42 grams per mole. So just to get some information out of this before we move on, it says it has an empirical formula of CH2. That's our simple version. So our empirical formula equals CH2. That's our simplest ratio. We're going to base everything off of that. Our answer will be some larger version of that ratio. And it also says it has a molecular mass of 42 grams. Now, molecular mass is like saying molar mass. That means it's the bigger version. It's the actual molecule. So that thing, our molecular formula, will weigh 42 grams per mole. Whatever our eventual answer is will weigh 42 grams. Right now, if we add up the C and the 2 H's, that does not weigh 42 grams. That's our simplest version. We want to find what our big version is. So we'll go step by step. Start the empirical formula. We did that already with CH2. Step 2 says find the GFM of the empirical formula. So now we have to actually do a little bit of math here. we're going to find out what this whole thing weighs. So my carbon, I see one of it, and if I go to my periodic table and look up what its atomic mass is, each carbon atom weighs 12. So the one carbon atom weighs 12. For hydrogen, I see two different hydrogens. So I write the two, and again, a periodic table tells me that each hydrogen atom has an atomic mass of 1. So I'm going to do 2 atoms of hydrogen times the 1 that each one weighs, and 2 times 1 is 2. Hopefully I'm not blowing anybody's minds with this math here. To find out what our entire thing weighs, our entire empirical formula, our simple ratio, we do the mass of the carbons, which is 12, the mass of the 2 hydrogens, which is 2, add those up, and I find that my entire grand formula mass for the simple version is 14. My CH2 empirical formula weighs 14. That just tells us what the mass of the small potato is. We still have no idea what the mass of the big bowl of mashed potatoes is. So we're going to do step 3 now, and we divide the molecular mass, which we were told is 42. That's my mashed potato bowl. Divide that by the gram formula mass of the empirical formula, which we just found down here. What did our CH2 weigh? And that is 14. So I do 42 divided by 14. Hit some calculator buttons if you can't do it in your head. And 42 divided by 14 is 3. Our molecular formula, our actual molecule, is 3 times larger than whatever our empirical formula was. Our empirical formula was CH2, so our answer is going to be 3 times larger than CH2. So I want to take this whole thing up here and multiply it by 3. And again, I can't just write a 3 in front because that just means there's 3 of it. So that's not going to be something I can do. But I will just multiply each individual element by 3. So that gives me, for the C's, times 3 gives us 3 C's. And for the H's, we do 2 that was there times 3, and that's 6. If you add this up, C3H6 should come out to exactly 42 grams per mole. C3H6 is going to be my molecular formula because it's 3 times larger than my simple basic empirical ratio formula of CH2. Third example, different numbers, same process. Do it same thing we've done step by step. Compound has a molar mass of 92.04 grams per mole. So that's again telling us our molecular formula. It all looks like that, molar. Our molecular formula, our big version, our mashed potato ball, weighs 92.04 grams per mole. That doesn't look like something that's going to be particularly helpful to us. We want to cross off those little decimals right there because we don't use numbers like that. We always round it off. So our molecular formula will weigh 92 grams per mole. We're going to simplify it to make it easier. We don't have to worry about that 0.04. And the empirical formula, it says, is NO2. So our simplest ratio is going to be NO2. So that's where we want to start here, because step 1 says start with your empirical formula. So I'm going to write NO2. That's what we're basing everything off of. Step 2 says find the GFM of the empirical formula. So for that, we want to add everything up. I see 1 nitrogen, so I'm going to go to my periodic table and see what that 1 nitrogen weighs. And my 1 nitrogen, I'm told, weighs 14 as an atomic mass. So 1 times 14 is 14, obviously. The oxygen part, I see 2 oxygens in my molecule. And again, the periodic table tells us that each oxygen weighs 16 as its atomic mass. So 2 times 16, and the 2 oxygens in this molecule account for a total mass of 32. We want to add them all up, 14 plus 32, and that's going to be 46. So that simple empirical formula weighs 46. Step 3, we divide the molecular mass by the GFM of the empirical formula. So the molecular formula, molecular mass, the molar mass, however you want to call it up here, that was 92. It's our big number. It's our big bowl of mashed potatoes. 92 divided by the empirical formula down here, its mass, so divided by 46. Ooh, switching colors, fancy. 92 divided by 46 will give us an answer of 2. That means our big molecular formula is twice as large as this simple ratio empirical formula, which was NO2. So I want to take this NO2 right here and multiply the entire thing by 2, scale it up by 2, make it twice as large, and that's going to give us a formula of N2O4. N2O4 is obviously twice as large as NO2 because we just multiplied every element in it by 2. And when we add this up, 2 nitrogens and 4 oxygens should come out to be 92 as a mass. So our final molecular formula is N2O4. Last example, we're going to start with green ink this time. I think we've earned that. We're going to treat ourselves a little bit. So number 4 says a compound has an empirical formula of C5H9 and a molar mass of 345 grams per mole. So our empirical formula, just as always before, C5H9, that means our basic simplest ratio is 5 carbons to 9 hydrogens. And our molar mass of 345 grams per mole means that the big version of this thing, whatever it ends up looking like, will weigh 345. If we add it all up, it should be exactly 345. We will now want to know what that formula actually is, what that compound actually looks like. What is its molecular formula? So just as we've done, step 1, start the empirical formula. C5H9. We have to be given that or we have nowhere to go from there. Number 2, find the GFM of the empirical formula. So just as we've done, we want to add the whole thing up. For the carbon part, I see that there are 5 carbons. I look up and see that each carbon weighs 12 as its atomic mass. So 5 times 12 is 60. For the hydrogen part, I see that I now have 9 hydrogens. We haven't seen a molecule as big as an empirical formula yet, but 9 times the 1 that each hydrogen weighs, that's a total mass of 9. We can add the whole thing up and find that our simple ratio, our simple empirical formula, weighs 69 as its molecular mass. That's what the entire small version of this molecule weighs. That's now on to step 3. So we're going to divide the molecular mass that we are told up here, which is 345, that's what the big version weighs, by the GFM of the empirical formula, that's this 69 right here, that the small version weighs. So we do 345 divided by 69. That's the big version divided by the little version. The big bowl of mashed potatoes divided by the single potato. And 345 divided by 69 will come out to 5. So that means our final molecule, our actual molecular formula, will be 5 times larger, 5 times heavier than up here the C5H9, which we now know has a molecular mass of 69. So we want to multiply this whole thing here, our whole empirical formula, by 5. And as I've said in every other slide, we can't just put a 5 in front because that just means there are 5 of that single small molecule. We want to make the molecule itself 5 times larger. So I'm going to take my C and my H, and we start out with 5 C's and 9 H's. We now want to multiply the whole thing by 5. So 5 times 5 for the C's, and that gives me, it gives me 25 C's in this molecule. And the H's, we start out with 9 H's, and multiply that by 5, and it gives me 45 H's. If we add this whole thing up, 25 carbons and 45 hydrogens, it should come out to exactly 345 as a molecular mass, a molar mass for the molecular formula. And that's our final answer, C25H45. It's a big molecule. It's a very large version of that simple empirical formula. But still, it has that 5 to 9 ratio. You see 9 is almost twice as much as 5, and 45 down here is almost twice as much as 25. So it keeps the ratio. It's just a lot bigger. And our final molecular formula is C25H45. So now I've done a couple examples. Make sure you finish the forms posted under this. Hopefully the video worked. You didn't actually have to go to YouTube. Otherwise, you're not going to be hearing me saying this. But make sure you complete the forms, and then we'll do some other stuff. We'll wrap this all up in class to really finish things off, but Unit 7 is in the books, and this concludes the unofficial first half of the year. Now that we have a knowledge and skills base, we can move on to real chemistry. And there's 7 topics left. The last 2 are kind of unto themselves and act as quick standalones to end the year, but the next 5 that we'll see build progressively off each other as a logical sequence of events. So strap in, and as I've been forecasting since day 1, prepare to ask for help.